Alright, it isn't particularly efficient to solve systems of equations by graphing. Obviously it takes me quite a while to enter the equations into my calculator, then I have to copy the graph down, and then I have to find the intersection of those graphs. And so we normally solve systems of equations using an algebraic method. Two useful algebraic methods are substitution and elimination. Now let's suppose that while you're doing one of these algebraic methods, let's suppose that both of the variables cancel out. That is to say that suddenly you've got no x's and no y's in the equation. If your remaining equation is false, like 2 equals 7, or something ridiculous like that, well then, that 2 is never equal to 7. That can't be true for any values x and y. Thus there are no solutions. And that must mean that the system is inconsistent. The lines are parallel. On the other hand, if both of your variables cancel out, and so you've got no x's and no y's left over in your equation, and you've got a statement like 3 equals 3. Well, that's always true. True for any value of x and y, and hence there must be an infinite number of solutions. And that infinite number of solutions is represented by the coincident lines because we have a consistent and dependent system. The lines are on top of each other. So let's talk about now the first of these algebraic methods, and we'll get a chance to practice these concepts if all of the variables cancel out as we're doing our substitution practice. Substitution involves isolating one of the variables. That's the key. That is to say, we will take one variable, put it by itself so we can express it in terms of the other variable. And then we will substitute that expression into the other equation so that it has been written in terms of only one variable. So before I go on, let's have a look at this process. So use substitution to solve the following systems. So I notice in my second equation, it's going to be very easy to get y by itself. So in my second equation, I'm going to write y is going to be equal to 5x minus 9. And now I will substitute the expression 5x minus 9. Because we know that this is equal to y, let's put this 5x minus 9 into the y of the first equation. So my y I will change into a 5x minus 9 equals 4. Now let's solve for the remaining variable, which is in our case an x. So 3x minus the 2 distributes. It's a negative 2 distributing, so be careful. And we got 3x minus 10x is negative 7x. The 18 on the other side, it becomes a negative. And so if I divide both sides by negative 7, this is negative 14 divided by negative 7. Hence x is equal to 2. And upon getting this variable, we will back substitute it into either of the other equations, or let's say the original equations is probably safest, in order to solve for the first variable that we originally isolated. And so I'm going to take my original equation, 3 times my x, which is a 2, minus 2 times my unknown y is equal to 4. And so I'll get negative 2y. If this 6 comes over to the other side, it becomes a negative 6. And if we divide both sides by negative 2, this is negative 2 divided by this negative 2 gives me positive 1. It's probably a good idea to also substitute it into the other equation too. This is an effective way of checking your answer and making sure that you haven't made a mistake anywhere in your algebra, that this solution 2, 1 does work. It obviously works in the first equation because we just found it. Let's see if it also works in the second equation. It's a way of checking whether my y is indeed correct. So negative 5 times my x plus my y value. Oh, sorry, I want to leave this as a y and see whether y solves to give us a 1 once again. You might not have done this checking technique, but it works well. My y, if it's isolated, becomes negative 9, and this negative 10 on the other side becomes plus 10, and hence y is equal to positive 1. You'll notice that because my y is equal to 1 both times, then that demonstrates that I must have done my algebra correctly, and so my final answer is x equals 2 and y equals 1. Now, over in this example, it's got three equations, and I've got an x, a y, and a z there. So let's begin by trying to substitute if I can isolate one of my variables. And looking down here, it's clear that the z is going to be very easy to isolate. I just divide both sides by 4, and I've got z alone. And fortunately, z is already a value that I can now substitute back into the first two equations to simplify this system. So in my first equation, I've got x plus y minus 3 equals 5. And my second equation, 2x minus 3y minus 3 equals negative 2. I've reduced the problem of 3 equations into a problem of 2 equations. And so now let's do the substitution methods again. Why don't I isolate the x in the first equation this time? And so that would give me x is equal to, my y on the other side is negative y. And if I bring the negative 3 to the right, it becomes a plus 3, giving me a total of 8. So I'll take this thing that is equal to x, negative y plus 8, substitute it in here for my x in my other equation. Never substitute into the same equation, or you're going to get 0 equals 0 every time, and you'll think there's an infinite number of solutions. The substitution method only works if after you've isolated a variable, you substitute that expression into the other of the equations. So 2 times our x expression, as we replace the x with the thing it's equal to, minus 3y minus 3 is equal to negative 2, and I'll try to solve for my remaining variable of y. The 2 distributes, and maybe I'll just bring the negative 3 over to the other side where it becomes a plus 3, negative 2 plus 3 equals 1. And that's negative 2y minus 3y, that's negative 5y. The 16 on the other side becomes a negative 16. 1 minus 16 is negative 15. And that shows you then that y is going to equal 3. When you divide both sides by negative 5. So now we know what the y value is. Let's substitute it back into the 2 equations that I was just working with up here. And let's substitute it into one of them first and see what the x value is. It's the only one I don't know yet. So my x plus this discovered y value of 3. And my z value we said was plus negative 3, so we substitute the plus z becomes a plus negative 3 equals 5. Nicely, the 3's are going to cancel, and so x is equal to 5. Let's also substitute it into the second equation and make sure that this is still consistent. So if I have 2x minus 3 times, my y value is 3, and my z value is negative 3, so plus negative 3 again, equals negative 2. So 2x minus 9 minus 3 equals negative 2. The negative 9 and the negative 3 together make a negative 12. If I bring them over to the other side and they become a positive 12, negative 2 plus 12 is 10. Divide both sides by 2, and x is equal to 5. And because my x's are the same in both situations, it's kind of like a self-check within the process. And I end up with a solution of x is 5. My y was 1. Is that right? I've lost myself. Sorry, y is 3, isn't it? And my z, I figured out, was negative 3. And so this is, maybe you haven't seen a set of 3-dimensional coordinates before. It is possible to graph things in 3 dimensions, where you've got an x-axis, a y-axis, and then imagine a z-axis coming out towards you, right out of the paper, perpendicular to the surface of the paper. And in 3 dimensions, we might be 5 units over in the x direction, 3 units up in the y direction, and then negative 3 units in the z direction, meaning we're moving 3 units away from you in the z direction. And then that point would be the solution to this system of equations. And incidentally, each of these equations, you remember how an equation which has got 2 variables, x and y, that's graphed in 2 dimensions and it forms a line? Can you guess what an equation in 3 dimensions with 3 variables is graphed as? The answer is that they form 3 planes. So if you imagine 3 pieces of paper, and one of them is perfectly vertical in one direction, and another one is perfectly vertical in the other direction, and the last one is perfectly horizontal, you can imagine that those 3 planes would intersect at a single point, and that's what we've got here, the point 5, 3, negative 3. Okay, a couple more systems to solve by substitution. So, looks to me like it might be easiest to get, say, the x alone in the first equation. X is going to be equal to the negative 4 comes across and becomes a positive 4. So let's substitute that in the second equation, y plus 1, 0.5. I'm going to go faster now because I think you probably have got the idea. And that means that y, so I'll distribute 0.5 times 2 is 1, 0.5 times 4 is 2, 0.5 times negative 2 is negative 1, and this plus 1 I'm bringing across to get another minus 1. The plus 2 and the minus 1 and the minus 1 cancel out, so I've got y equals y. If I bring them to the same side of the equation, I get 0 equals 0. So my x had disappeared through my substitution process, but when I simplified my final equation, or my resulting equation, I end up getting my y's cancelling out as well. I got 0 equals 0. What does this mean? It of course means that this is true for every value of x and y, so I have infinite solutions. If I have infinite solutions, that means that my two lines are on top of each other. They're coinciding lines. And we know that we can describe a set of solutions, coinciding lines, to all of the coordinates x, y, such that, and you could use one of the original equations, 2 times the y coordinate is equal to x minus 4. That's the rule for all of the lines that are on top of one another. So I suppose if we had isolated the y in both of these cases, and in the second one, I've got 0.5x, that's like the same as half x. 0.5 times negative 2 is negative 1. The plus 1 comes over. Look, they're identical equations. Of course, I didn't use substitution there, so here I have used substitution and followed the required method. And let's do some substitution again. Let's see, it looks like it might be easiest to isolate the y in this situation. So 2y is negative 3x plus 4, and y then must be negative 3 halves x plus 2. Substitute that into the second equation, and my negative 9 I'm going to distribute here. And now let's distribute the negative 6. That gives me a positive 18 over 2 and a negative 12. 18 over 2, of course, was 9, and minus 9x. And then we've got minus 9 equals 1. Do you see it? 9x minus 9x. The x's cancel. Negative 12 minus 9 gives me negative 21 is equal to 1. Ridiculous. This is never true. There are no values of x and y for which this will ever be true. So this represents, of course, two parallel lines. They are, you don't need to write this down if all we're looking for is the solution, but I just want you to be thinking about what graphically this means. And so then, well, that's really all I can say. In this situation, because there were some solutions, I was able to express what those solutions were. Over here, there are no solutions, and that's really the only thing I can conclude about the situation. We got parallel lines. I'll just introduce the idea of elimination before we go on to the last video of the lesson. So elimination means that we're going to rearrange both equations into standard form. Now in this first example, they're both already in standard form, ax plus by equals c, so no rearrangement will be required. And then we want to multiply through one or maybe both of the equations by constants, such that the coefficients of these numbers in front of the variables, for one pair of variables, maybe the x's or maybe the y's, we want these coefficients to be the same. And if they are, then we can add the equations together or maybe subtract one equation from the other in order to eliminate that variable. So, for example, maybe you want to sort of multiply one of the equations by 3 so that you've got a 3y in one equation to match the 3y in the other equation. Or maybe you want to multiply one equation by 2 and the other one by 4, and you've got a 4x and a negative 4x, which is also a kind of matching pair, which is opposites. If they're equal, we'll subtract one from the other. If they're opposites, we'll add the equations together.